Welcome to Work Package 3 of the CIRBAT project. This work package accounts for modeling and simulation of the electrolyte interface. The lead partner of this work package is the University of Liverpool, whereas the partners involved are Johnson Matthey, the CIC Energy Cune, Università de Camerino, and the CNRS. The contributors to this work from University of Liverpool are Ivan Scivetti, speaking, Ben Morgan, and Gilberto Teobaldi, who is the work package owner. In addition, we had the contribution of Charles Delacorte from the CNRS and Javier Carrasco from the CIC. Let's start this presentation with a brief introduction to the problem we want to study. Our research is in the context of lithium-ion batteries. Lithium-ion batteries constitute an environmentally friendly technology of energy storage. Like any other battery, lithium-ion batteries are composed of the following main elements: the anode, the cathode, the electrolyte, which is the medium that separates anode and cathode and where lithium ions move, driven by the electrochemical forces. And finally, the external connector that allows electrons to flow from the anode to the cathode and vice versa. Lithium-ion batteries work thanks to the electrochemical intercalation of lithium ions. This means that lithium ions are inserted and extracted from the anode and the cathode in a way that is reversible. The goal of current research is to improve the performance of lithium-ion batteries to meet future energy demands. So we want lithium-ion batteries to become more efficient, to deliver more power and to last longer, and also to become less expensive, less heavy, and more benign to the environment. In order to achieve this goal, we need to get a deeper understanding of the many mechanisms that take place inside lithium-ion batteries. In particular, the CIRBAT project aims to improve the fundamental understanding of the structure and reactions at the electrolyte interfaces. As the name indicates, the electrolyte interface is the region where the electrode, anode or cathode, is in contact with the electrolyte. Chemical reactions at the electrolyte interface often lead to the formation of what is called solid electrolyte interface, SEI. This research is indeed very challenging. In fact, electrosurfaces are complicated chemical environments. Chemical reactions do not only depend on the nature of the electrolyte and the anode and cathode materials, but also are affected by surface morphology, impurities, defects, etc. For these reasons, experimental results are still not conclusive. Within this framework, modeling and simulation provide an alternative tool to investigate the reactions at the electrolyte interface. And this is the strategy that we have followed in this work package 3. Computational research involving lithium-ion batteries can be divided in two different approaches: the first principles approach and the continuum analysis approach. In the first principles approach, we need to solve the quantum problem for the electrons, because in this work package we have considered transition metal oxide materials. We have chosen to solve the electronic Schrödinger equation via the Hubbard version of density functional theory, often known as DFT plus U. On the other hand, matter is treated as a continuum in the continuum analysis approach. This means that equations describe macroscopic quantities. In this work, we have used the shuttle model of oxidation reduction. Whereas for the first principles approach, we need high performance computing, in the continuum analysis approach, a single processor is often enough. With first principles simulations, we can get a fundamental insight of the problem. However, studies are constrained to hundreds of atoms, zero voltage calculations, and ideal models for crystals. If we follow the continuum analysis approach, we can simulate problems involving a larger length scale and more realistic scenarios, like simulations of battery evolution, for example. However, results may strongly depend on the model and input data for the various properties. Ideally, both approaches should complement each other, and both approaches should feedback with experiments in order to improve theory and models. With more sophisticated simulations, the aim is to guide the implementation of experimental solutions. In this work, most of the research has been carried out using the first principles approach. Let's now start with the research overview of this work package 3. We first consider lithium titanate, that has been identified as a promising candidate of anode material to be implemented in the next generation of lithium-ion batteries. This is because lithium intercalates at a relatively high voltage, thus avoiding the formation of lithium dendrites and consequently reducing the risk of short circuits inside the battery. In addition, lithium titanate exhibits a negligible structural distortion during lithium intercalation. This gives an improved structural stability in comparison to other materials. This material also has a high rate capability, low toxicity, and lower cost. Upon the insertion of lithium, lithium titanate transforms to a phase that is called lithium-7. Using DFT plus U, we investigated on the structural and electronic properties for these two phases in bulk. By considering other phases, we could also investigate on the thermodynamic stability for this material. Experiments suggest the formation of a new phase at the surface of lithium-7, which is called alpha lithium-2. For these reasons, we have built several interface models for alpha lithium-2 and lithium-7. With these interface models, we investigated on the electronic screening. In addition, we performed electronic characterization and carried out charge and geometrical analysis. In the second part of this work package, we analyzed in detail the alpha lithium-2 phase. In addition, we studied lithium manganese oxide, which is a good candidate of cathode material to be implemented in future designs. This is because lithium manganese oxide has a high operational voltage, is lighter for a given capacity, it has a low safety charge, it has a lower cost, and it is environmentally friendly. However, this material undergoes degradation that affects its lifetime. Using DFT plus U, we could investigate on the bulk properties for these two materials. This allowed us to obtain a detailed insight into the use of different approximations for DFT plus U. In addition, we obtained valuable information of the electronic structure and energetics for these two materials. Particularly crucial to the case of lithium manganese oxide, we also evaluated the role of the magnetic ordering. Using the information we obtained for the bulk properties, we then investigated on the vacuum exposed surfaces for these two materials. We computed the electronic structure and energetics for various surface facets and atomic terminations. The lowest energy surface for alpha lithium 2 is the 100 lithium oxygen titanium terminated. On the other hand, for lithium manganese oxide, the lowest energy surface is the 111 lithium terminated. From the distribution of manganese cations within the lowest energy surface of lithium manganese oxide, we could obtain unprecedented results of the disproportionation reaction, which is believed to be the reason behind the degradation of the material. We finally computed the role of defects for the 100 alpha lithium surface. From the research of the vacuum exposed surfaces, we then evaluated the role of the solvent. To this purpose, we considered two different examples of electrolytes, ethylene carbonate, EC, and dimethyl carbonate, DMC. Here we see examples of the absorption pattern of EC molecules over the 100 alpha lithium surface and the 111 lithium manganese oxide surface. This study allowed us to evaluate the changes in energetics and electronic structure upon the absorption of molecules. In addition, we could carry out analysis of the charge transfer between the electrolyte and the surfaces. In the third part of this work package, we used the knowledge of the solvent exposed surfaces to evaluate the role of inserting extra lithium to the system for lithium manganese oxide. We first consider the effect of lithium intercalation, that means lithium inside the surface, and here we display two different surfaces for lithium manganese oxide, the 101 and the 110. We later considered the effect of co-adsorption, which means inserting lithium as part of the solvent. Based on these results, we could provide new insights on the factors that govern lithium diffusion and aging. Finally, in the fourth part of this work package, we consider the effect of coating and passivation. Coating is a very important experimental strategy to avoid the degradation of materials. For the particular case of lithium manganese oxide, coating has been shown to be crucial in helping to extend the lifetime of the material. Here, we have built several models to study the effect of alumina coating on lithium manganese oxide, LMO. Using DFT plus U, we could evaluate the role of the coating on the energetics, electronic structure, and charge transfer. In contrast to all the previous results that were obtained using first principle simulations, we have applied continuum analysis to investigate on the SEI passivation over porous graphite. In particular, we have used the model of shatter oxidation and reduction. This study provides new insights on the evolution of graphitic carbon anodes. At this point, we arrive to the end of this informative presentation. For more information, you can visit our webpage.